Welcome to MIT 307 Numerical Analysis class. In this lecture, we are going to start learning numerical methods for ODEs. We have seen earlier how one can compute derivatives numerically. This was from our previous lectures. These calculations often resulted in expressing differentiation with an approximation method. In this lecture, we introduce numerical solutions of ordinary differential equations. Derivative formulas that we have found previously will be used directly in this lecture. We will replace derivatives with the numerical derivatives that we have found earlier. First, let's consider an initial value problem in this form. So to find the values of the function, the x, this is the unknown function here is the x, and the x is a function of t. So what we need is finding xt at some point. So say we need the function value x at t is equal to 2. To that end, one can solve the problem analytically first, and then substitute the value t is equal to 2 in its formulation. This is one approach. However, finding an analytic solution is not an easy task, or even impossible for vast majority of initial value problems. Okay, so for this reason, the practitioners have to find numerical solutions to these ordinary differential equations instead. So we work with numerical solutions of ordinary differential equations. In this direction, many methods have been developed and continue to be developed. Computation techniques for ODEs are mostly motivated by the approaches we investigated earlier for numerical derivatives. So let's first consider the following initial value problem. So here, in this example, a formula for the derivative of xt is given with an initial value. So this is the derivative of f with respect to t, which is the only independent variable, and also an initial value x0 is equal to 2 is given. So suppose that the function xt is linear from 0 to 2. We can easily find the value of this function at x2 in this particular case if we have an assumption that xt is a linear function, since both the slope and a point that the function passes through is given, because if this function is linear, which is our assumption, we know it's not linear, but this is an assumption to give us some idea about how to approach this sort of problems. So we have the slope, the derivative, and also a point that the linear function passes through. So in this particular case, we can find an approximation, linear approximation to the function x, and say this linear approximation will have the slope m is equal to x1 minus x0 divided by t1 minus t0, which will be equal to the derivative. So the derivative will be equal to the x value at 2 minus the x value at the initial point 0, and the difference between the t values will be equal to dx dt. This is again with the assumption that the function itself is linear. In this particular case, we can solve for x2, and this will give us a solution to x2, and this is only with an assumption that the function is linear. But as seen from the derivative formula itself is also showing that this function x is not linear function. Okay, but this was just an assumption. Nevertheless, we can still use the same approach with a slight rearrangement. So here we assume that the function is starting from 0 to 2. So between the interval from 0 to 2, the function was linear. This was our assumption. But instead, assuming the function to be linear on some interval, instead of assuming that the function to be linear on the whole interval from 0 to 2, we alternatively let it be linear on a small interval from 0 to h. Okay? Instead of assuming that the function is linear everywhere, we can assume that it is linear from 0 to h only. Okay? Then this h is much smaller than the final time 2. It still comes with an error. Of course, the function is not linear, but we assume that the function is linear on this small interval. But even if it comes with an error, this error is now tolerable and depends on the value of h. And this h, as you know, a user selected an adjustable quantity. Okay, so if we can find the error with respect to h, we can modify, adjust the value of h to obtain maybe better accuracies or smaller errors. Following the same idea, we can obtain an approximation to the function value x h immediately, because this is linear function. Okay, so we assume that the function x is linear from 0 to h, and then we have the slope, because this is the derivative of x, and this will give us the slope, and also we have a point that the linear function passes through, so then we can find xh immediately. Consequently, we are one step up on the stairs, okay, which motivates us to follow the same pattern for x of 2h and so on. Okay, so if we consider the moving from, say, we are, if time t is equal to 0, then say we are at this point, and then for example, if we have the xh value for small h, this will give us, this will move us from original initial value to somewhere else, which is closer to, of course, 2, right? Because say this is 0 and original initial value, and say this is 2, we basically jump on this interval as h increments. Okay, so we have given the function value at this point, but here using this linearity argument we can find solution at this point. Okay, so if we have the solution at this point, which is something that we have just found, and we can jump on the solution to the function value at 2h. Okay, and then we can follow the same pattern, and then following this pattern, so we can obtain the value of the function at 3h using the function values at 2h. So this will basically move us to get this point and obtain the function value at t is equal to 2. Okay, so this is the idea. Okay, consider equal spaced points 0h, 2h, 3h, and so on. And finally, we will arrive at nh, which is equal to 2. So we have n steps, and with h increments, we have equal spaced points on this interval from 0 to h. This points will start with 0, and with h increments, we will arrive at t is equal to 2. Okay, so this will be a partition of this interval. As mentioned above, we can find approximation to xh, x2h, and so on, and finally x and h with linearity assumption. Start with an approximation to xh, for example. Since xt is not a linear function, the expression below is only an approximation to this quantity. Okay, so linear functions have the same slope everywhere. Okay, so if you consider a linear function like this, for example, it will have the same slope everywhere, either at this point or that point. No matter which point you choose to compute the slope, it will give us the same answer. But the function we have is not linear. Okay, so for this reason, we need to choose at which point we will take the derivative. Okay, we will evaluate the slope. Therefore, at what point we take derivative is now under consideration. So there are two candidates. The one will be if we are moving from 0 to h, the first candidate will be the evaluating the derivative at 0. The second candidate will be h. Okay, so there are two candidates. We have 0 and h. To proceed, assume that we take the derivative at the left end point, which is equal to 0. Then we obtain this formulation for xh indeed. So this will be equal to slope, and we evaluate the slope at the left end point, which will be equal to t is equal to 0, and its corresponding x value. So this will give us the slope, and we will use the formula for the equation of linear functions to get xh value indeed. So in this expression, this is known because we are given this function, and also x0 is known. H is something that we have predetermined, so this is also known. So xh can be found immediately. This is just for solving xh, we get this expression. Okay, so these are all knowns. Okay, the last approximation looks very similar to the equation for a line segment with a known slope and a point that it passes through. So this is the slope. Okay, and this will be the indeed, if you for example say h is equal to 0, this will be the point where this it's passing through. Okay, so this is very similar to the equation of line segment. Okay, so we have found an approximation to xh. Okay, given x0 and the derivative values and h, we can find an approximation to xh. Okay, so this is one step up. Okay, if we follow the same idea, we have obtained an approximation to quantity xh thus far. Using its value and following the same idea, we can proceed to find x2h by this formulation. Okay, so then we have found xh value, so we can use this xh value to determine the slope. Okay, and then we multiply the slope by h, just like we did before, and then we add this value to the previous function value. This way we can obtain an approximation to x of 2h. Okay, so in general, if we proceed like that, in general we will obtain this formulation. So x of kh will be equal to x of k minus 1h, so this will be previous solution, plus h times the right hand side function evaluated at the time is equal to k minus 1h, and x will be values will be used from the previous solutions. Okay, so repeating the same formula, we can find an approximation to the value of x of 2. Okay, so increasing with h increments, we can arrive at t is equal to 2, and using this formulation we can obtain an approximation to x of 2. Okay, so consider the given initial value problem again. So the initial value problem is this one. Okay, so we consider this initial value problem and try to find x of 2. Okay, this is what we started with. Okay, so using the same formulation, as if h is equal to 0.5, then x of 0.5 will be approximated by x of 0 plus h times the derivative. So this will be 0.5 times derivative at t is equal to 0. So I just put 0 here for time, but we also this function is has two variables, x and t, but we just put the t values here. That means this function will be evaluated at xt comma t. Okay, so this will be evaluated at x0 comma 0. Okay, so when we evaluate the function at x0 comma 0, x0 was, what was it? X0 was 2, so this will be sine 2 minus 0 over 2. Okay, so this will be sine 2, 0 over 2. So this will be slope times h plus the initial value, and that will give us 2.4546 for an approximation to x of 0.5. Okay, so we have found an approximation to x of 0.5. We can use this information to get x of 1. Okay, so this will be using the same idea again. X of 1 will be approximated by x of 0.5 plus h times the function value at t is equal to 0.5. Okay, when we do that, this will be copied from the previous solution. So this is the previous solution, and we evaluate the function value at t is equal to 0.5, and x is indeed equal to x of 0.5. Okay, so it is also given here. Then we obtain this approximation to x of 1. So this will be an approximation to x of 1, and then using this approximation we can find an approximation to x of 1.5. Okay, so this will be basically, this value will be copied there just like here, and then its value will be used to evaluate the right hand side function values again, and we also choose we also know t values will be 1, so we put the 2h, which is t value in this case, so here in the right hand side function, so we can obtain an approximation for this quantity like that. Okay, so lastly we can use this information, basically this outcome, and using this we can obtain an approximation to x of 2, and it will be equal to that. So this is the idea, and this is an example for evaluating the solving ODEs, initial value problems, numerically. Okay, next example, solve the following initial value problem using the proposed method with step sizes of h is equal to 0.4, and it will be halved 1, 2, 3, 4 times, and lastly we compute that with h is equal to 0.025, and then we choose time is equal to 10. Compute the error and relative error using the true solution. Here in this case we have given the initial value problem, the initial value, and the final time is 10, and we are also given the true solution. So this is the true solution. So we use all this information. We indeed have the analytical solution. So this is the true solution here, but we just try to solve this ODE numerically, and then use this exact solution to find an error for the method itself. Okay, so also it says observe the ratio by which the error decreases when h is halved. So h is halved everywhere. So what is the error with 0.4 and what is the error with 0.2? So we take the ratio of the errors with this quantity and that quantity and see if there is a pattern with this decreases in the errors. The following code solves the problem and computes error on MATLAB. So this is the code itself. Okay, so the function, the right hand side function is t times e to the negative t minus x. which is t times exponential negative t minus x. So this is the forcing function, the right hand side function. And then the true solution is equal to 1 plus 1 half t squared e to the negative t. So this is the true solution. Okay, so the forcing function f, the right hand side function, and this is the true solution. We need true solution to compute error, and h is chosen 0.2 in this particular case, but we can modify this to obtain various results for various h values. And t0 is equal to 0 because it's starting from 0. And capital T is for final time is equal to 10. And then we say, let's take the increments of the interval. So we start the Tn values from 0, and it will go all the way up to 10 with h increments. So this will be basically 0, h, 2h, 3h, and so on. So this will give us the time values or the partition in the from 0 to 10. And then we predefine this approximate solution. So xh are our approximate solutions, and we predefine them with zeros everywhere and on this vector. And we know the size of the solution will be equal to the size of Tn. Okay, so we basically record we save all the solutions from 0 to 10, and all the steps will be given here. Okay, so this will be there for visualization purposes. Okay, so you will have a plot for the solution at the end. Okay, so xh1, which is the first solution, the first approximated solution, but in this particular case it will be the initial value and it's exact. So let's take it to be x of t0, which is the true solution at 0, and this will also give us the initial value already, which is 1. Okay, so if we substitute 0 there, this will be equal to 1. Okay, so this is we initialize the solutions, and we say n is equal to length xh, so n will be the number of steps. Okay, and then we start our loop with index starting from 1 and going all the way up to n minus 1, and this index will be like the k we used here. So here the k value will be here, so k times h will be this will be corresponding to index times h in this particular case. Okay, so we basically have xh index plus 1 is equal to xh index, the previous solution, plus h times function value f at tn index, comma xh index. So we evaluate the slope at the previous function, previous solution. Okay, and then we multiply that by h, and we add the result to the previous solution to obtain the new solution. Okay, and when we do this, when we loop over all the index values from 1 to n minus 1, that will give us xhn at the end. Okay, so the error will be equal to the absolute value of the true solution at 10, x of 10, minus xh, the computed solution, which is a vector, and the last component of the computed solution. So the last component of the computed solution will be an approximation to the x values at t is equal to 10, and this is the exact value. So we take the difference, and the absolute value of this difference will give us the error. And also relative error is equal to the absolute value of this difference divided by the the computed solution at the last component of the computed solution. Okay, so this is the code. What does this code give us if we change h values? So first we choose h is equal to 0.4. When we do that, this will be equal to the computed solution. This will be our computed solution at t is equal to 10, and the absolute error will be equal to this quantity, and the relative error will be this quantity here. And if we take the half of the h values instead of 0.4, if we take 0.2, then xh value, the computed solution will look like this, and the absolute error will be this quantity. Okay, and then this is if we take the ratio of these two, this will be close to number 2. And again, this is the relative error, and this is again the relative error with 0.2. Again, if we take the ratio of these two errors, we obtain something close to 2. Okay, if we take h is equal to 0.1, we take the half of the previous h value. Okay, then the error will be this will be the computed solution, and this will be the error. As you see, if we take this ratio, this will be close to 2 again. And again, if you take the ratio of these two errors, this will be equal to 2, or approximated by 2. Okay, so if we follow this pattern, and if we take halves of h every time, we observe that the ratio will get closer and closer to 2. So this means if we take the half of h, error will be half. Okay, so reduction in h is proportional to the reduction in the error, because the accuracy of this method is only order of h. Okay, also we have given the plots of the approximate solutions and true solution. So the true solution is given with given in red, and the approximate solution is in blue. As you see, h is equal to when h is equal to 0.4, they are not that close. They are still close, but not that close. There is a big gap here. And if we take h is equal to 0.1, the difference between these two solutions will be still apparent, but not that much. But if you take, for example, h is equal to 0.025, this is quite small compared to these two numbers. Their difference will not be identified. So they're almost the same. I mean, not exactly the same, but we cannot visually see any difference between these two. Okay, a definition. After that point, a definition given an initial value problem in this form. So the derivative is equal to f of x comma t, and x0 is equal to x naught. Various methods to solve this problem are as follows. So this is the forward-Euler method. The forward-Euler method is the method that we've been working on. Xn plus 1 can be found by xn plus h times f of xn tn. So here the known values of xn and previous tn value can be used to find the slope, and then we multiply that by h, and this will be the update on the solution, and the previous solution will be updated with this value to get the next solution, the solution at one step above. Okay, so this is forward-Euler method, and we investigated and we worked with this in this lecture already. The backward-Euler method is also given here. The difference between forward and backward-Euler method is in the evaluation of the function values. we evaluate the function value at the next time step in this backward Euler method. So here we use the previous values of the solution and Tn to obtain forward Euler, and here we are using the information from the point that we are about to arrive. So xn will be here on both right hand side and on the left hand side, both on the left hand side and on the right hand side. Okay, so this is backward Euler method, and forward Euler method is itself first order accurate method, and backward Euler has first order of accuracy, and trapezoidal rule will be given with this formula. So we approximate the slope at the pretty much the average of the two slopes. So this is this is how we find the slope on the left end point, and this is how we can find the slope at the right end point. If we take their average, we obtain the trapezoid rule, and it is h squared accuracy. So this is a second order method to solve ODEs. And here we have midpoint rule. In the midpoint rule, we evaluate the slope at the midpoint. Okay, so this is the midpoint in the x values, and this is the midpoint in the time. So this will give us a slope again, and we update the new solution by h times the slope again, and this will give us midpoint rule, and this midpoint rule is again second order accuracy method. Okay, remark: the forward Euler method is explicit. By explicit, we mean the unknown is only function of known values. So this is known and that is known. So we can immediately use this values and obtain x of tn plus 1, which is the unknown. But in this particular cases, so in this three cases, xn will be both on right hand side and left hand side. So here and there. So the forward Euler is explicit, while the rest of the methods are implicit, because xn plus 1 are on both sides. Therefore, one can compute the solution with the forward Euler method explicitly, which means we can compute the solution immediately. However, the other approaches require solving for xn plus 1. Solving for xn plus 1 is not a problem if the function f is a linear function of x. But if it is not a linear function, then we need to use solution techniques, numerical solution techniques like Newton methods or bisection methods, maybe, or maybe fixed point iteration can be used. This sort of ideas has to be employed to get updated solution for these three cases. Okay, an example: find an approximate solution to the following initial value problem with the backward Euler method, and step size is equal to h is equal to 0.25. Okay, so this is the initial value problem, and this is the derivative of x with respect to t, and x0 is equal to 1. This is the initial value, and what we want is x of 1. So what is the x value at t is equal to 1? So this is the question mark. We consider the formula, this formula. This is from backward Euler method. With the initial value, x0 is equal to x naught, which is equal to 1. Okay, so here the function f is 2x minus t, which is linear and at x. So that means we can immediately solve for xn plus 1. So let's do that. X1 will be equal to 1 plus h times 2x1 because it used to be x0 and 0 here, but since we're using the forward Taylor method, this will be x1. This is for n is equal to 0, for example. x1 will be equal to x0 plus h times x1 f of x1 comma t1, and x1 is here and t1 will be 0.25, so it is substituted there. So x1 can be updated or found by this number and with this formula. Okay, since we have x1, we can use x1 values to obtain x2. In this formulation, if we choose n is equal to 1, then x2 will be equal to x1 plus h times f of x2 comma t2. So x2 will be equal to x1, which is found from here, x1 plus h times 2 times x2 minus t2. t2 will be equal to 0.5. Okay, so this way we can find x2, which is here. Again, if we choose n is equal to 2 here, then x3 will be equal to x2 plus h times f of x3 comma t3. So it will be found by this formulation, and x3 will be approximated by this quantity, and then x4 will be found by using again this formula with n is equal to 3 and x3 is equal to this quantity. If we substitute all these values here, x4 can be found like this number. Okay, so this is our numerical solution for x of 1, and x of 1 can be approximated by this quantity. Therefore, an approximation x of 1 is approximated by 12.75 can be found. Choosing h is equal to 0.25 allowed us performing computations by hand, but resulted in a too much defect in the solution. So this is something we can achieve by solving by doing computations by hand, but in reality this is not accurate enough. Okay, the accuracy in the solution is in trouble. Okay, so on the other hand, one can find the solution, the approximated solution, by, for example, computing on MATLAB with h is equal to 0.001. This is quite small if you compare this to h values. As h value decreases like that, if we choose h as this small, then the solution will be, the approximated solution will be this quantity. And as you see, this quantity is not even close to that number. Okay, so this is a much better result for x of 1. If we similarly use h is equal to 0.0005, which is half of what we used here for h, and in this particular case, x1 will be approximated by this quantity. As you see, as h decreases, like this quantity and that quantity, x1 values will get closer. Okay, so the error here in this particular case, for example, maybe in starting from the second decimal place, maybe, because they are the same up to first decimal place almost. Okay, so that will conclude our lecture, and this will give us a brief idea on how to solve ODEs with numeric techniques. You need to do all these computations on your own to have enough understanding on the subject and gain some practice, do some practice and gain some experience with this approaches. That will conclude my lecture. Thanks for watching carefully.